Good day, everyone. So we're going to go over Chapter 4 today. Here's the thing: is that with Chapter 4, I'm only going to hit the highlights that I think that you might see in another class or potentially in the media. All right. So let's say that we had two variables: lung cancer and whether this person smoked habitually throughout their lives. All right. Now, just like with regression analysis, there's going to be an explanatory and a response variable. All right. But remember how we labeled the explanatory with an X? Well, we're not going to do that here. And we're not going to label the response as a Y. And the reason why is because, remember, we did that because we had a scatter plot, we had two axes, and we can visualize this with, you know, by graphing it, okay? Here, we can't graph stuff, okay? Why? Because the variables here are categorical, okay? They're not quantitative. Um, Now, since since we have to go ahead and label these as one is the explanatory and one is the response is figured out for this problem. So smoking is the explanatory. That came first. Okay, person decides whether to smoke or not. All right, that came first. And then lung cancer is the response variable to it. Okay, in response to the smoking or not. All right. And so we're not going to set it up in a scatter plot, but we can analyze this with the table. And what we're going to do is we're going to put the response variable and its different levels as the columns and the explanatory as the rows. All right. And so for this particular example, we would have lung cancer because that's the response variable as the columns and the explanatory as the rows. Now, could you switch them around? Yes, but all the formulas that we talk about would change. And so just to keep things consistent and that everybody's doing exactly the same thing, so we don't have to change any formulas around, we're going to set up the response as the columns, explanatory as the rows. All right, so let's say that we randomly sampled 1,000 US adults, and after we did that, we found 26 had lung cancer and smoked habitually throughout their lives. Uh, we found 199 that that did smoke, okay, but didn't develop lung cancer. Okay, we had 225 that smoked habitually throughout their lives. Okay, we can do exactly the same thing for those that didn't smoke. Okay, and we come up with totals down there. Okay, for lung cancer, so there was 30 people in total that had lung cancer, 190 that didn't, and then we had 1,000 people. Okay, so now a person was either in this group, that group, that group, or that group. Okay, and so they're in one of those four cells. So if you this cell, this cell, this cell, that cell. Okay, can't be in two cells. Okay, and everybody fit into one of those cells. Okay, so now in Intro 2, we will figure out mathematically why these two variables are related. That is not our focus here. What our focus is going to be today is all about risk. Okay, now I do this for the benefit of my future medical students because medical students and if you become doctors or nurses or whatever, nurse practitioners, you might have to talk about risk, and certainly the medical field talks about risk all the time. Okay, risk of developing a certain disease. Okay, I do this also for everybody else so they can critically evaluate news stories because media will often present risk. Okay, so now risk is the proportion or percentage of people in an undesirable category. Okay, and so since it's the proportion, it's going to be a fraction, right? And so risk uh, is equal to the number of people in undesirable category. That's so notice number of in the numerator divided by the total number, right? That would give us a proportion or a percentage. Then if you wanted a percentage, you would multiply it by 100%, right? So the question is, what is the risk of getting lung cancer if you smoked habitually? So if you smoked habitually throughout your life, so what did we do by saying if you smoked habitually is that we've isolated this group, okay? So basically what we're saying, out of this group of 225 people, how many developed lung cancer? That would be 25 over 225. And it turns out to be what? 11.6%. Okay, so that would be the risk of smoking. Okay, all right. So what do you think would be the next thing to do? Well, we're probably going to go ahead and focus in now on those that didn't smoke. So notice here that didn't smoke habitually. So now we're focusing in on what? That group right there. Okay. So what is the risk of developing lung cancer if you didn't smoke habitually? Well, we had 775 in that group. And out of that group, 4 developed lung cancer. And that turned out to be 0.5, 0.5%, excuse me. So that's a pretty big difference between the two, 11.6% versus 0.5%, right? So 11.6 versus 0.5, big difference, okay? And so, so to evaluate the difference between the two, we go to the next topic here, and that's the relative risk, okay? The relative risk is the division of two risks. So what's the numerator here? The numerator is the risk of the least desirable level of the explanatory variable, okay, and divided by the risk of the more desirable level, okay. So what's the least desirable level? Well, the least desirable level in this case would be smoking habitually. Why? Because they had a bigger percentage of people that developed lung cancer. So this is the least desirable. That would be the numerator, okay. And then the risk of the more desirable, that would have been this one because they had a smaller instances of lung cancer, okay? And just as a note here is that if you ever hear the word baseline, okay, baseline is the denominator and is the risk of the more desirable level, okay? So let's go ahead and figure out the relative risk here, okay? So notice I put the 26 divided by the 225. Now I did this as a fraction because if you do it just with the percentages, you get rounding error. Here you're not going to get any rounding error. So I just use the actual numbers, 26 divided by 225 divided by, then the 4 divided by the 775. And you're going to get a number of 22.4. Okay, that would be the relative risk here. Okay, now we have to define exactly what that means then. Okay, so the math's not too hard. Okay, let's make sure that we understand what that means. So relative risk is 22.4, and what does it mean? So the interpretation of the relative risk is that a person is 22.4 times more likely of developing lung cancer if you smoke versus not smoking. So 22.4 times more likely of developing some sort of disease if you do this versus that. And that's a lot of times how the media presents it. Not every time, okay? So a lot of times they don't give you the two separate risks. What they're actually telling you a lot of times in the media is the relative risk, okay? You hear this a lot, okay? You hear it a lot. And that's what I basically said right there, okay? All right, now I want you to check this one out. The administrators at UC Davis decided to present this in a slightly different manner. So what I want you to do is I want you to click on that hyperlink there, and it'll take you to a website. And what it was trying to tell students is why you should wear a mask around campus. Okay, read it for like I don't know, like a minute or two, and then come on back. Okay, just kind of get the gist of it. Okay. All right, assuming that you have read a little bit about, you read the website there, okay? Let's keep on going. So instead of presenting the relative risk, the administrators decided to state it as, the administrators just stated it as how much the risk of contracting COVID could decrease, and according to them, by 60%, 65% if a student wears a mask. So they didn't present it as a relative risk, but they're still presenting it as a risk, but in a different way. Okay, so what exactly are they saying here? Let's do some simple math first. Let's start with a number of 200. Okay, and what does it mean to decrease it by a certain percentage, right? So if this number decreases by a small amount, say such as 1%, it won't go down much, right? And actually, if you do the math there, so if you take the 200 times 0.01, you get 2. So what that means is that it's going to go down by 2. All right. And so instead of starting with 200, the number now is 198. So therefore, if the number went down 1%, is now 99% of the original number. Okay, so certainly these two things are related to one another. Okay, how much is going to go down and how much is it of the original number? Okay, all right. Let's say it went down 50%. We know the new number is 100, right? If it goes down 50%, we know that, okay, if it started at 200, now it's going to be at 100. Okay, so when it decreases by 65%, it's more than half, right? And so if you do the math there, 200 times 0.65, that's 130. Okay, so that means it's gone down 130. So the new number is what? 70. Okay, and so a decrease of 65 means the new number is 35% of the original. See how they're related to one another? Okay, it's 100% minus the decrease. Okay, and uh, that'll give you an idea what the new number is going to be. Okay, of the original. Okay, so now let's apply it to this particular issue here with COVID. Uh, and let's work through the math here. So I'm right here. Okay. Let's pretend I do not know what these actual numbers are. The website didn't state it, and I didn't look it up. Okay, but let's just pretend that the risk of getting COVID without a mask is 0.001, so 1,000 out of a million people. Okay, the website is stating that this number decreases by 65% by wearing a mask. What does that mean? Okay, well, so you take the 0.001, multiply it by 0.65, you get this new number here. Okay, this is the actual difference. This is the difference. Okay, that's the difference. And so the risk of contracting COVID with a mask is actually what they're saying is that if this is uh, with a mask, I'm sorry, without a mask, okay, and um, your chances of getting COVID goes down by 65%. Okay, so let's do the difference there. This is the risk of developing COVID with the mask. Okay, pretty small, right? So I just went ahead and presented it like that instead. Okay, so I think instead of a thousand people out of a million getting COVID, it would be 350 out of excuse me, let's see, what was the numbers I originally, oh, instead of 1,000 out of a million people getting COVID, this would be 350 out of a million getting COVID. Okay, so the risk decreases by 65%. Now, what does that mean in terms of relative risk? Relative risk is that, remember, you would have the risk of the more undesirable on top, all right, divided by the risk of wearing a mask. And so we got here 2.86. That would be our relative risk here. Okay. So they could have stated it like this. Your chance of getting COVID is 2.86 times more likely if you don't wear a mask. Okay. So they could have stated it like that, but they decided to say it as mask cuts risk by 65%. Now, in your mind, which one is more powerful? Well, obviously, the folks at UC Davis thinks that by saying this is a more powerful statement and it'll get across to people. But a lot of times the media will present it like this, and I don't know. That's sort of up to you. Which one is more powerful of a statement. Okay, you decide. Okay, um, but that's what's happening there. Okay, so I just wanted you to relate the two. Okay, that if someone tells you that, hey, the risk decreased by this much, you can still figure out the relative risk. Okay, and vice versa for that matter. Okay. Okay, let's keep on continuing on here. Um, so you got to put a critical ear to all this, especially in the media. The media tends to sensationalize things that sound really serious. Okay, now I'm not saying COVID isn't serious. Okay, I'm not saying that. I'm just going to give you a different example. Let's say, by the way, this is a real disease. A disease called, and I'm not even going to try to pronounce it. Okay, this is a real disease. Okay, and you get this disease from a worm that's found in Central Africa and some parts of South America. Okay, And the media could say things like this: you are 300 times more likely of getting this disease if you visit Central Africa versus South America. Well, yikes. Maybe I shouldn't go to Central Africa then. My goodness, look at the difference here, right? Look at the relative risk, right? But remember what I told you is that a lot of times the media is only giving you the relative risk. They're not giving you the individual risks, okay? And let's read through this. If you actually look it up, the risk of disease in Central Africa is 3 in every 1 million people. And the risk of disease for South America is 1 in every 100 million people, okay? So, in other words, even though they did give you the right relative risk, they didn't tell you what the individual risks were, okay? And if they told you what the individual risks were, maybe it's not so dramatic, okay? So you got to be careful of not being too easily swayed by news media, okay? You really need to sometimes look deeper, okay? And not just hear what they're saying and saying, wow, there's a big risk of this happening, okay? You got to look at the individual risk to really assess what's going on. They're not lying about the relative risk, okay? They're just not telling you what the individual risks are, okay? Then you can make an informed decision. Last thing that I want to go over is Simpson's paradox, okay? And what is Simpson's paradox? The direction of relationship or difference is reversed within subgroups compared to the direction of the relationship within the whole group. Okay, sounds kind of weird, all right? So the direction of relationship or difference is reversed within subgroups versus the whole group. Okay, so now I'm going to go over and use some numbers with regards to batting average. Now, I don't care if you like baseball or not. I, um, it doesn't matter if you know anything about baseball. Okay, uh, it really doesn't matter in this situation. I promise. Okay. Now, batting average, what it is that it's just an indication how well the batter is doing. Okay, and the way you calculate it is the number of hits divided by what we call number of at bats. We'll just say that it's the number of successes they had out of total sample size. That's all it is, just like any other proportion. Okay. And so, like I said, this is the most common way of determining a batter's effectiveness. The higher the batting average, the more effective the batter. Okay. And so a batting average, because it's a number between 0 and 1, a 0.3, okay, or what they would call 300 batting average in the major leagues would be considered an above average batter. Basically, the batter's getting a hit 30% of the time. Okay, that's actually pretty effective as far as a batter goes in the major leagues. Okay, all right. So I gave an example here where in the first half of the season, so as you can imagine, there's starters and there's backups. Okay, and the team prefers to have their starters in, right? And so when you took a look at the first half of the season, they had a batting average of 254. Okay, the backups had, as you can imagine, probably had a lower batting average. They had a batting average of 238. Okay, so these are the two groups: the starters, the backups, and the team average turned out to be 0.249. So they had a 249 batting average overall for the team, first half of the season. Now, in the first half of the season, we'll say that they had a fair amount of injuries to their starters, and so the backups had to play more than maybe the team wanted. And then maybe the starters got over the injuries. Okay, and let's see what happens in the second half of the season. So the second half of the season, the batting average actually went down for the starters. It went down to 252. So it went from 254 down to 252. The backups went down from 238 down to 235. So you're saying to yourself, okay, the starters went down, the backups went down. Of course, the team went up. Yes, it actually goes up. It went from 249 up to 251. And just to sort of prove it to you, if you figured out the total year batting average, notice that the total team batting average turned out to be 250. Okay, so it went from 249 up to 250, but within the subgroups, oh, it went down. How in the world did that happen? But it's absolutely true. You can check out all the math. Okay, it actually happened. All right, this is the reason why it happened. Is that in the first half of the season, when the starters had a batting average of 254, okay, they had 70% of the at bats. Okay, they had 70% of the attempts. Okay, in the second half of the season, when there was less injuries, they had 90% of the attempts. Okay, and that 90%, okay, overcame the fact that their batting average went down from 254 down to 252. Okay, so because they proportionally had more at bats, okay, than the backups, okay, that weighted more on the batting average. Okay, and so I showed you one way of calculating a batting average. Here's another way if you don't believe me here. So the batting average for the first half of the season, you got 70% times 0.254 plus 30% times 0.238, it comes out to the 249. Well, if you do exactly the same thing and you do that weighting, okay, 90% versus 10%, batting average actually goes up, even though within the subgroups itself, it went clearly down. Okay, so that would be an example of Simpson's paradox. Okay, what happened here is that you had differences in total sample size between two groups as you went through the season. Okay, so the direction of the relationship or difference is reversed within subgroups. What happened in the subgroups? It went down. Okay, but the direction within the total group actually went up. Okay, Simpson's paradox. All right, well, thank you for your time.